talk will be given by Akshay and Saurabh, which I hope I got right. And I'm very happy to introduce them because earlier this year I had the opportunity to meet both of you actually in Bangalore, and it's been very fantastic to see the local Clojure community in India and just hang out with so many people you wouldn't otherwise meet because there is a lot of distance between those two communities. You've traveled for, I think, 5,000 kilometers and many hours. I heard there's some other people who came from Japan, so the award for like the longest journey, you kind of missed it. But I think it's still a worthy contender. So yeah, please give it up to Akshay and Saurabh and enjoy their talk.
So we're just going to be using these mics, so I hope we're both audible. Saurabh, you want?
Is this audible?
Cool.
All right, cool.
Let's start.
All right, let's start. Hello, I'm Saurabh. I work at Go-Jek.
Hi, I'm Akshay. I work at Nilenso. I used to work at Go-Jek with Saurabh in some of the stuff that we're going to talk about, but I don't anymore.
All right. So, and our talk is about reducing accretion in monoliths. So let's go over a bit of background first. So a large part of Go-Jek's business is about the ride-hailing. So where you select a pickup and destination, you select your payment method, and then you order a ride. But before that, you have to go through all this. This is because these are some 18 plus of the products that Go-Jek has. Because Go-Jek is a super app which has so many products, and all of them need to scale independently. Currently, we are doing somewhere around 100 million plus completed orders every month. And we have had insane growth over the last 3-ish years. And we have just about 200 plus engineers managing all this. So just wanted to set up some context before to understand our problems.
So a lot of the products that you saw on the screen, maybe 3 years ago, were really just a single product. They were just a single code base. Everything was put into one place. Even though now, as it stands, there are explicit boundaries between each of these products in terms of teams and code bases, they expectedly didn't start out that way. We were just a one thing. And as you mentioned, as the product grew in scale and requirements, the single service style architecture started proving to be too restrictive and became quite massively bloated over time. So think about just like 18 plus sitting in a single place. It's extremely hard to manage. So months after that, a lot of what we did was just deal with fire as we saw like unprecedented growth. And it was just us trying to like get out of that stage. So one of the obvious things that we did were to tease apart the products into different teams. Since each of the products demanded scaling up in isolation, so it made sense to have these teams work on their own products and their own code bases with like separate API endpoints and different data stores and such. But we know that this is a hard problem. Like migrating systems is a hard iterative process, and so was this. These were slowly teased apart, but they continue to call back into the legacy system. And they still do. There are still remnants of various subproducts just talking back to this monolith in 2019. The products now have sort of split apart, but that doesn't necessarily mean that the number of dependencies have fundamentally reduced. Each of these products continue to want to do the things that they need to do at a bare minimum. So like some of the things that a product would do would be send notifications to customers and drivers if their like cab has arrived and such, tracking a ride on the screen, allocating the drivers themselves and processing their payments. This is, of course, not an exhaustive list. There's a dozen other things that a product usually tends to do at Go-Jek. So if you look at it from the outside, this is a bit of a mess. We've pulled out all these products into their own systems. And as an organization, we've decoupled ourselves. But on a product level, the dependencies necessary for them to continue to function start to accrete. And on top of that, we still have a connection made to the original monolith. And the product that has been teased out is sort of starting to become a legacy system in itself. So if you think about this as a tree, if at the top, there is the org, and then there's the products as the leaf nodes, and there's the dependencies of those leaf nodes. We felt like there was some dependency accretion building up. So a lot of this talk is us trying to solve this problem.
So what were some of the problems that we faced due to accretion? This is typically what a ride-hailing booking lifecycle looks like, where you create a booking, then a driver is on the way to pick you up, the customer is then picked up, and then the booking is completed. And out of the first two states, maybe either driver or the customer can cancel. This resulted in the ride-hailing OMS being a cluster of dependencies with various dependencies for various functionalities. We'll keep coming back to this over the course of the talk. Some of the problems were that maintaining 99.9 percentile uptime allows you only 43 minutes of downtime per month. And at Go-Jek scale, it's even a few minutes of downtime can result in huge monetary losses. Of course, developer productivity is affected, which could have been applied to work on features which would have given exponential returns. And there is the loss of trust from the customer, which is also very high. A monolith is effectively too many responsibilities in a single service. What that tends to result in is that it is a system which is hard to reason about because nobody knows what all this service does. A result of some of these things is that, for example, the database starts to grow in size. There'll be one table with too many columns in it, or that table will be huge. Or even if we had asynchronous job using the Sidekick framework, which one of the ways it uses it is Redis. So there'll be too many jobs which are running, and all of them are in the same Sidekick. So that becomes suddenly a critical Sidekick. Another thing is that onboarding people is hard because they have to get all this context and know exactly what all this service works. So getting them to work on, understand the system and build new stuff is hard. Deployments also become really hard. For example, you can imagine, let's say, one API takes about 30–40% of all the throughput that you have on a service and requires 15 VMs to run. Now, let's say you want to work on a piece of code which is completely independent of this API, but you still have to deploy all those 15 VMs because you don't want to have deployment drift. Otherwise, debugging becomes a nightmare. So that is a challenge. Writing integration. So typically, even we did as the first step was to cut down monoliths into small services which call each other synchronously. That also resulted in a problem that we ended up like having 200, 300 microservices, all of which call each other. So even to complete a booking flow, that results in multiple API calls to multiple services. And even when you're writing integration or regression tests against this sort of distributed system, even if one of these API calls fails somewhere, your test fails. And that results in a lower confidence in the tests. And as a result, somewhat of that confidence in that test suite itself can drop. So for us at Go-Jek, literally it was reduced dependencies or shut shop because that's the nature of, because these systems were so critical.
Just to talk about the dependencies a little bit, what we're talking about here is responsibilities and concerns. These could just be microservices, or they could be databases, or they could be actual functionalities that are dealing with various parts of the product, like sending push notifications or driver incentives, or keeping monetary audits in the OMS itself. So we realized that one of the good design choices that we made early on when we pulled out this product from the legacy monoliths was to start sending facts about the booking lifecycle that you saw earlier over to Kafka. We figured that the pub sub model sort of is a very straightforward way of reducing domain logic managed by a single service and distributing it to multiple services which are independent of each other. We also realized that a lot of this sort of side ancillary work that we were doing wasn't really updating things back to the OMS, so it was sort of detached in a sort of respectable way, which means they could be easily moved away from this kind of a system. So we started to realize that this model should, in theory, help us solve some of these problems. And as we build these consumers that read Kafka events, we can just reduce over the facts and do useful things. If this model were to truly work, processing payments would be a big win because it's one of the more critical flows that exists in any of these products. But we just simply started out with moving out notifications, which is like sending notifications to customers and drivers out first as one of our test benches.
So we started out with notifications. So we focused on these two dependencies, the push notifications and the sidekick Redis, which did the job processing. So this is what our system looked like before splitting. When a API call used to come into the order management system that a driver has been found for a booking, it would typically queue a notification job into the async job framework, which would then call the push notification service, which would send out the notification. The async job's responsibility was to know when, so the order management system here is knowing when to send a notification and also doing stuff like fetching the customer's locale so that the message can be localized for the customer. What we wanted to move to was a system, something like this, where the order management system doesn't know about these notifications at all, but simply emits facts on a stream saying that a booking has been updated, and then a stream notifications service can pick it up and then actually perform sending the notification. All right, so how does this look in practice? To set up streaming with Kafka, you'll need something like a topology that you have to set up. This has a couple of parts. The Kafka stream setup is the first part, where in the first three or four highlighted lines, you can see that we are setting up a stream builder, we are configuring the pattern to it, and then after that, we are logging some custom metrics to know, for example, how many messages were processed and so on. And then there is the business logic, which we say that which type of log do you want to read? How should that be converted into a map so that that can be used further? And then maybe there is some filtering of some certain types of events. For example, you could say, I don't want food events. I want only ride-hailing related events. And then there's finally there's the notification logic, which we here have written as a dispatcher. And it goes to something like this, where we used multi-dispatch it came in handy a lot here. And we could use it to essentially switch on the event type that was being broadcasted, so that we could say that if a driver has been found, send a notification that your driver will arrive in 5 minutes. If a ride has been completed, then you can send out something like, thanks for riding with Go-Jek. Or not do anything for events where you don't want to notify the customer. So before this, this was sort of what the notification code looked like. You don't have to actually read most of it. It's just stuff that you wanted to show to give you a sort of feel of how it was before and then what did it come to. So this was the booking class, which when the state transition happened, it used to know that I have to send this notification out. Then we would gather details for the jobs like the customer's locale. Then the job would be queued and it would call this other class, which would be actually responsible for calling the push notification service, which would send out the notification. And after moving to stream processing, this was a much cleaner business model specific that we code that we moved to. This is, of course, just the business logic. There is ancillary code of connecting to Kafka and fetching driver location, locale, and all that separately. As you might have noticed, the order management system was in Ruby, and we shifted to Clojure as our choice for this new service. That was because for a couple of reasons. First being that we wanted Kafka stream since we already had Kafka set up, and interop was very easy to do. We also knew that essentially what this consumer is going to do is it's going to read a map of Kafka and then transform that into another map, which would be used for creating a side effect. For example, read an event, transform it, use that as params, and make it and perform an API call or put it in a database somewhere. So this kind of operation fits very well with a functional, with any functional languages. And we already had a few devs in our org who had written large-scale systems with Clojure. So this was a natural fit for us. So basically, with this migration, we got rid of this dependency. Then we took a step back and thought about, hey, to make this service, we had to write a lot of code to connect with Kafka and all that stuff. And we also see that we have to repeat this pattern for multiple other use cases. So can we extract some of this boilerplate out? And now that we want to, and can we now really get to the most critical part of payments, and can we use this sort of a model as well to solve that problem?
So that's actually what we did. The payments dependencies are roughly this. You can see them on the pink is what it looks like on the screen. It requires payments, Postgres, and still making connections to the old legacy monoliths. And we want to try to remove this as well from the OMS, so that there's less and less responsibility for the OMS. The pre-split system, much like the stream notification system, looked like this, where there would be an async job, which would just make a transaction and call into the payment system. And the next move was basically just, again, send an event out. A service would read that event and make the payment system, thereby decoupling the payments processing bits from the OMS itself. However, this time around, the payments processor, the service that we're talking about, we didn't sort of handwrite it from scratch. We actually built a small library or maybe a framework, I don't know which one, around this boilerplate work of stream processing. So basically, like the Kafka stream topology, the consumer topology, all the error handling, reporting, the lifecycle. We use Mount internally to manage the lifecycle. All of that sort of baked into a single place. And the code starts looking like this. We unfortunately don't have any like the previous code version of Ruby for payments processor, but we'll just show you what we have now. The interesting bit is over here, which is the main line. This is where we call into Ziggurat, which is the framework. We pass it a main function. This main function is the function that you would define for your consumer. This function would be called each time an event is received via Kafka onto your consumer. Typically, you would put like the normal processing stuff here. So over here, we're checking whether the booking is for transport or not, and then we're handing it over to process, which will do other things. Like if it's canceled, it'll reverse the payment. If it's completed, it'll make the transaction to the payment system. Some of the internals behind this, the main function that you saw sort of works like this, roughly, where the first part of it is just validating whether the stream routes that you specified are accurate. And it also does all the heavy lifting of making the Kafka connection. It has a bunch of error handling logic here, which is necessary in case things really go bad. So the processing function, the mapper function that we saw previously, is sort of passed over to something called a mapper func. which is a part of the Ziggurat library itself. It's a higher order function that wraps over the client FN that you see here. What it wants from the client function, which is basically your consumer, is a whole bunch of keywords that you can return. So it's sort of frameworky in that way where it needs you to return some of these things quite specifically. So if you say success, it'll report a metric and like guarantee that it worked correctly. You can choose to skip the message, and block is currently not implemented. However, there's like one missing, like a core missing concern here. You can read the message, treat it as successful, or skip it. But what really happens when the message processing fails? We can simply retry, but what if the retries also fail? So when things are all good, in practice, you would receive an event from Kafka. Ziggurat would take it, pass it over to your actor function. It would do the work, and then return a success keyword, and then Ziggurat will know that everything is good. What you can do now when everything is not so good is return the retry keyword instead, the thing that you see in the red, and it'll go into its retry mechanism. The retry mechanism works simply like this, where if there is a retry received by Ziggurat, it'll push it to a delay queue. All of this, of course, is all configured. It's configurable. You can configure the delay queue to be backing off exponentially or linearly, however you want it. It'll take that message, put it in the delay queue, and after a certain amount of time, it'll put it back into the instant queue and give it back to the actor function to process the message. If the number of retries are exhausted, which is also a configurable value, it'll go into the dead queue, from which you can make an API call or just sort of sort through data and figure out which ones were completely failed. So if you see, the only real things while you're writing a thing with Ziggurat is just the semantics of these three keywords, which is success, skip, and retry. There's nothing else to learn here, really. You just sort of get the library and do these three things. Basically focus on writing your domain logic and nothing else. However, we didn't actually just sort of put this system into production directly. We ran both the systems in parallel. The reason we could do that is because the payments are inherently idempotent. So we ran them in parallel. We had audits checking whether the two things were doing the right thing. And so it sort of looked like this, where we continued to send the transactions from the async job to the payment system, and we were also piping it to Kafka. And payments processor was doing the same thing.
All right, so we have processed payments and moved a very critical part of our system to this framework. So basically, we went mad with it and started removing a whole lot of functionality and transitioning to this framework, library, I don't know what to call it. And so in addition to customer and driver notifications, we moved the payments. We also moved ride tracking, which is a key functionality in any product that we have. So this is what the original dependency graph looked like. This was the changelog, essentially. The ones in green are the ones that were directly removed. The ones in yellow are the ones where functionality of that piece of software is reduced. So for example, we moved audits out of the order management system into this other service. So we could remove that table from Postgres, similarly with Sidekick, Redis. This was the resultant graph that we just had a few core components that were required for the ride-hailing OMS. So what were the benefits of doing this migration? System is more resilient. For example, we are not relying on that one Redis somewhere to ensure that payments work. We have moved to a much more resilient model, which is also a fact-based system, so you can replay those events. The system is more easier to reason about. We have split it into separate services, each of which has a single responsibility. So if I see a service saying payments processor, I know exactly what it's going to do, instead of one large service which does 15 other things. less code, less functionality means less code in a service, lesser number of tables in the database. We dropped 100 GB payments audit table from a service. Testing is easier because now, for example, if I want to test that our payments going through, I don't need to generate the entire booking lifecycle flow. I just need to make a reservation, publish an event saying this booking has been completed, and then check that the payments processor has processed the payments. Deployments are easier. As we talked about earlier, we had a huge number of VMs on the order management system. But now if I want to make changes to, say, the push to the notifications part or the payments part, I don't need to deploy to all those 50 VMs. I just need to deploy to those 2-3 VMs serving that, which are used by that particular service. As I said, we moved a lot of functionality to what we call to these actors. So we built about 51 actors over 6 months. Even stuff like the ability to chat between a driver and a customer, that was moved to this framework. One of the ride tracking functionality was also moved, and that requires that service to process the current location of the driver, which meant more than 2 million messages per minute were being processed by this system. So yeah, yay.
That's actually pretty much mostly what we have around this story for this. Keep in mind what we're talking about started off about a year ago, and we've gone quite a bit ahead with this venture of ours. So we just want to take some time and spend it on demoing you what Ziggurat looks like in practice. We have it's a very blazing fast video. It'll finish in 2.5 minutes, so just keep your eyes glued on the screen. Let me attempt this. That is indeed not playing on my screen, so I'll look at what you saw is basically the 2 prerequisites dependencies that you need. You'll go ahead and create a new repo. We called it Ziggurat new here. We've checked that it exists. We'll add the Ziggurat library here. We added logging also for good measure. Now we're just going to run line depths. That was very quick. It's 1.5x speed. So this is a huge blob of a config Eden file. It uses clonfig behind the scenes, so a lot of what you see is sort of clonfig-like mechanisms. The focal point here is the Kafka configuration that we're doing here. It will set topics, the bootstrap servers, the stream threads, and another thing that I can't really see from here. I guess that's the topic. Yeah, and we have a whole bunch of RabbitMQ configuration here, some retry configs here, and that's actually pretty much it, all you need to configure. So this is one of the protobufs that we're using. It's just a simple protobuf with 2 fields. It has a text field and the font name. We're going to try send a message in the text field. We're going to add a library called clj-figlet, which will let us use the font and display the little text that we're going to be sending from a Kafka producer. This is, again, the code looks quite similar. We have a start function here, calls into Ziggurat, and then it passes over a main function which checks the message and prints ASCII. The print ASCII function is just a call into clj-figlet. It picks up the font name and then just renders that. So quite straightforward. We're just going to test whether we have the font files available. We have them. Just going to test the REPL. That works too. We have a small Kafka producer just running here as another Emacs session, and we're just going to send another message to the specified configuration that we've mentioned in config Eden. We're just going to send a message here. If you've owned a cat, you know this is true. And that just sort of shows up here. And I'm going to send another message that will also show up there, as expected. And that's pretty much it for this demo. So yeah, it was just a quick foray into what it might entail to get this working. It's quite straightforward. A lot of the heavy lifting is already taken care of. But there's something worth noticing here, which is the shape of the code, if that's the right word. the shape of the code that kind of comes out as a consumer is quite similar to each other. Like most of these consumers tend to be very same. They just have this like processing function that takes an event, it does some dispatch work, and then either returns a success or returns a skip if it doesn't want to process it, or returns a retry if it can handle that. So the shape is quite consistent. So all the 51 odd actors that we have, they all look very similar. So it's very easy to get into doing this. And these are, again, the only 3 things you really need to learn about. All the boilerplate around monitoring, alerting, retrials, the retrial strategies. It also comes with a built-in web server if you need to make calls to it. And the lifecycles, there's manage my mount, all of that sort of comes built into it. So maybe what I'm saying, I guess, is more like a framework and not a library. So all the heavy lifting is abstracted away. Just some clarification on the terms. This is not an agent by the Clojure definition of things. This is clearly not an agent. It is also not an actor because it doesn't really produce messages yet, and some of the other considerations, I mean, given the correct definition of actor, this is not one of those. So what I like to sort of tongue-in-cheek sense call it is a loaded, spoon-fed Kafka consumer. It just is doing a lot of things for you. This is also not a toy project. There's an active community that is working on this. It's currently 8 active contributors. The helmet guy is me. It's open source. You can please check it out. Give us suggestions, file bugs, use it. I can help you out around here if you want to try it. But of course, not to like paper over these things too shockingly. It does not do certain things. It can't, as we said, doesn't produce any messages. It has to be idempotent. Your consumers need to be idempotent, otherwise this will not work. Or, well, you'll get into bad situations. And coordinating multiple events transactionally is extremely hard. Distributed transactions are hard. And it's going to be hard to do this. So if you're doing things like what you're doing, we were previously doing in the OMS, where we had everything in one place, the transactions were simpler, they're now harder as a result of this. What we also figured was that this was a great way to teach Clojure in some ways. Like a lot of heavy lifting has been abstracted away. So you can just focus on writing the domain logic and in turn build some useful stuff and then learn some more Clojure and then build some more useful stuff. So if the argument for, I don't know if there'll ever be a Rails for Clojure, and I don't know if there should be one, but if the arguments for Rails are valuable, then some of those arguments also apply here. Some of you might have also noticed and figured that this sounds a bit like a lot of these things that already, all these free and open source software that already exist. There are some key differentiators here. The link pointed below has done quite a bit of research into how it's different. But it tries to solve a very specific slice of problems. It comes packed with the independent retries. It's quite opinionated about the message transmission protocols. And you don't really require any clustering of itself. You just need to manage Kafka, which hopefully you're already doing it in a big place. Depends, I guess. Yeah, I guess that's pretty much it from us. Thank you.
Thank you very much. That was very insightful, and I think it's always interesting to see how people like take the Clojure mindset of reducing over events and all that kind of stuff like to the next level, and how it's helped in your organization. Maybe you're all excited for a coffee break, but maybe also some people here have questions. So I think we have time for 3 questions or something like this. I see a first one here, so let's do it.
Thank you very much for the talk. Very often in a monolith, you have a lot of hidden, ugly dependencies. And when you started to think about which part you could move out of the monolith, how difficult was it to really understand the boundaries of what you could move away, even if you had the team knowing the software by heart?
Yeah, maybe I can take this. Some of us obviously know the code better than the others. Fortunately, for a lot of the dependencies, as we mentioned, we grew really fast. So even though we got bloated over time, the amount of time it took us to get bloated was short enough that a lot of things were fresh in people's heads. So I guess we were able to navigate that. But I don't really have a good answer to like a DAGE to follow here. But if you follow good object-oriented practices, maybe the things are already decoupled in your system and relatively easy to tease out. Yeah, I don't know if
maybe.
Yeah, maybe. Yeah, it is a hard problem to do. It took us quite a bit of time to move these things out.
And a lot of debates on what should this be in this service or not, or so that kind of, there's a lot of debates that will happen in your team, so brace for those.
To add to the response, these guys, I also work with these guys. So there was a really nice suite of integration tests and a set of audit tests that these guys had written for the services. So even if the some parts of the code that were missed when we extracted something out, that was caught very well in the integration tests and the audits that they wrote.
Testing.
Yes, that's correct. Yeah, we wrote quite an aggressive auditing suite around most of these migrations that we did. Basically ugly audits, really, just actually peeking into the database, checking if things are correct and all that.
Okay, more questions.
Hi, thank you for the talk. How did you cope with the schema evolution, and especially with when your schema changed in such a way such that the previous messages were invalid in the new schema?
You're talking about the schema sent over Kafka?
Yes.
Yeah.
Yeah, so we sort of had a internal library that was the central library that was used by all anyone who wants to publish an event, and it was managed in sort of managed by a team, and you couldn't, for example, drop a message, so that all messages were always backwards compatible. So it never broke as such. But yeah, that was sort of done manually. There's not a really great way to automate that to prevent people from introducing breaking changes. So.
Yeah, just to add to that, what a repository gives you, we call it log entities, is just a collection of protobufs, is versioning. You get versioning just within the repository itself, and all the new changes that come in are pull requests. And so they are sort of manually validated, but they are validated before coming in. And we have a policy of at the moment, not really removing any fields from an event, so just append-only events, essentially. So new data is coming in, maybe some data is getting stale. The team that Saurav was talking about also keeps a track of who is using the events. And so if there are consumers who are not consuming a part of the event, they would sort of know. This is, again, also done manually. But just a simple way of dealing with this is to version it and just be append-only, I would say.
All right, thanks for the question. Second to last question, so whoever wants to go after this, better raise your hand early.
Hello, thank you very much for the talk. Sorry for my question, but maybe there's a lot to learn from that. I seem to remember there is still a legacy system. So what couldn't you get rid of?
Sorry, when you mentioned there was a legacy system in the dependency graph?
You had some picture where the monolith was in the middle, and then you said this is now out of it, but there's still a legacy monolith.
Right. So we dropped that basically. So all the green ones here are the ones that we dropped, and then we ended up with something like this. So where the legacy monolith is now gone. So we did manage to remove that.
It was unfortunately called Stan Marsh.
Yeah.
And I'm not quite sure who named it, but it's gone now.
Dead. Okay, last question. Okay, I'm lazy.
Hi, thanks for the talk. Usually when you build a monolith, you want to process everything synchronously. And in the end, when you switch to stream processing and distributed systems, usually you will have to switch to asynchronous user interface as well. Did you do that as well?
Yeah, essentially the first step that we did after trying to split out the first monolith was that we created a bunch of services which called each other through APIs. But then we saw that that was also not a scalable approach, because any one of these APIs failing caused the whole system, the whole flow to break. So we essentially moved to this model of publishing facts, and for example, the publisher doesn't have to know who all the consumers are and what is the responsibility that's going to happen. So the publisher, for example, an order management system will just say, okay, a booking has been updated or booking has been completed, and it will just announce that to the world, and then all the other services listen for that event, and then they sort of react to that by, say, processing payments or sending out notifications or sending out an email receipt and stuff like that. So we did move to a more asynchronous model.
I think the question might have been more around how the user interface works, like when you press a button and then it sends off an event, and then you end up with something where you don't immediately get the feedback from the server that it has been successful, stuff like that. But I would encourage you to just get together and hash it out later on.
There is a good answer. Yeah, we can catch up.
But yeah, it's an interesting problem that you certainly encounter with these kinds of systems. Okay, it's coffee break time. Coffee is served downstairs. See you here later, and enjoy the coffee break.